Okay, let's finish the last bit for the course. Still about the proving the correctness of loops. We're pretty much done. I just want to do a few more examples with you, and then we'll talk about the exam. Okay? All right. So, just a few announcements quickly. There are 2 review sessions for the exam. I already announced that on the Moodle. Please confirm your attendance for on the Moodle, because otherwise, if we got too few people, I may just collapse the 2 sessions into one. Okay? So make sure you sign up for that. So one will be 2 to 4, Thursday, the day after tomorrow, and also 11 to 1, Friday.
Do we have lab tomorrow?
Lab tomorrow? No. Tomorrow is a fall study day, so you don't have any school. All right. So there's no lab tomorrow. Okay. So 2 to 4, and then 11 to 1, and make sure you confirm your attendance. It's in Lausanne, Lecture Hall C. Okay. And as for your marks, I'll try to make them all available around the exam day. I'll definitely try that, okay? I know it's coming, okay? However, what I will guarantee, once you see your marks after the exam, I will give you a few days to come to see me to discuss any issue you like. Lab test, labs, whatever, or even exam, okay? But it's coming. Okay, now, let's review what we said about the contracts for loops from last time. A very quick review. Basically, the 2 things we learned about loops contracts was, one thing is about invariance, which is a Boolean condition we check. And also another integer expression, which is called variance. Okay, we got looping variant, we got variance. And we talk about how you can check it, right, at the runtime. Okay? Basically, you have to make sure the invariance is already established after the very initial step to establish the looping variant, right? That's the first thing to note. And also, as soon as you actually violate the looping variance after the end of any iteration, you're going to have the looping variant violation. And then for the variance, it is going to be checked at the end of every iteration over there. And then you want to make sure the variant expression is larger than or equal to 0. If it is not, you're going to have a loop variant violation. Okay? We did go through a very simple example last time, which is quite trivial, but just to illustrate how it works. Any question about how the looping variant and variant work in general before we see some more complicated example? Okay, okay with this? All right. Okay, what we will do is we'll do one example together. Okay, let me just show you some slides quickly. So this is the program we want to consider over here. Okay, basically this program here. Let's just go over one line by line very quickly. So this program over here is called find max. We want to find out the maximum for the array. So we give it an array of integer. We want to return an integer. Okay? And then we declare local variable I for the loop counter. And then over here, initialize I to be a.lower. And then we say the result, the maximum should be initialized to be ai. Okay, a at position a.lower, basically. And then we have a looping variant over here. We'll consider that in just a moment more closely. Also, we got an exit condition here to say as soon as I is strictly larger than a.upper, we're going to exit from the loop. For every iteration, we're just going to see if the current element is larger than the result, we're going to replace the maximum, and then we're going to increment the counter as well. Okay? And then the variant is going to be a.upper minus I plus 1. Okay? It's an integer expression. And in short, the post condition over here is to say from a.lower until a.upper, we actually got the result larger than or equal to a at position j.item. Okay? It's a more complicated example than what we discussed before, but it's still not very hard. But now we want to see how we can justify the appropriateness of the looping variance and variance. Okay? Now, let's now have a look at that very more closely. Okay? What I would do is, okay, that's looping variance and variance. Okay? Now, let's consider the following combination. Okay, what I want to have is something like this. Okay, I'll show you on the iPad over here. You know, I'll try to make it a little bit larger over here just to show you. Okay, I want you to pay attention to 2 stuff over here. One thing is about the loop invariance over here. This is the loop invariance, which is specified using an across. And this is the loop variance using this integer expression over here. Okay. If you look at this particular looping variant variance, can you already spot any issue? Do you think the looping variance and variance are okay? Or none of them, both of them are not okay? have a look at that and try to see if you can spot any error. But we're going to trace it all together. Okay? I'm going to show you actually in total, you'll see on the slides we've got 3 versions, right? We want to see for each version you're given whether or not the contracts for the loops are actually appropriate. Okay, for this one, anyone want to speak out? Go ahead, yes. Okay, you're suggesting I minus 1 for which one? For looping variance or variance? Invariance? Okay. You're suggesting over here for what? You're suggesting I minus 1. Okay, you're suggesting this. So why would it be wrong originally? Let's now try to make it more concrete for you. Okay? Let's say we are considering a particular array over here. Let's say this array. Let's say this is A. We got 4 elements there. A dot lower is pointing to the first element, A dot upper pointing to the last one, right? 20, 10, 40, 30, right? Something like that. So we got 4 iterations to go in total. Now, if you're claiming that we should change looping variance upper bound from I to I minus 1. So when is it going to fail if we use the original looping variance? Why? Why would it fail? How exactly does it fail? Let's sketch the idea verbally, and then we'll trace it all together. Okay? So now let me just wipe it out. Exactly what you just suggested over here. I can tell you that it's actually correct, okay? But we want to know why. This looping variant as is going to fail at some point. Why is it going to fail? Okay? Can you tell me exactly which iteration is going to fail? Not either you or others in the class, doesn't matter. Yeah, go ahead.
The first iteration before it enters the body of the loop.
Okay.
Yeah. So it says before entering the body, the result.
Okay. Okay, you're saying, you mean before the first iteration or after the first iteration? Make a decision, because before? Okay, how about let's do this all together, and then we'll see if you're right or not, and then I will get to you. Okay? So now, let's say this is the looping variant we have over here. Let's not change it, okay? So now, what we'll do, let's trace it. I have a table over here, okay? If you have access to the slide, try not to peek. Let's look at that together. Okay, so now we'll do the initialization over here. So the initialization is going to be, we initialize I to be A dot lower. Let's say it's 1-based array, like in your lab test. So I is going to be 1. So what about result? What's going to be the result? 20, right? That's going to be A at position 1 in that case. Okay, it's going to be 20. That means the maximum we established to begin with is 20, the first elements. And is the looping variant going to satisfy though? Okay, how do we see that? Okay, let me just do this one for you. Basically, what we're going to do is we're going to substitute I over here just by 1. Agree? Because currently I is of the value 1. It's corresponding to the following mathematical expression. Let me just do it over here, right? It's going to be for every j such that a dot lower less than or equal to j less than or equal to, and I is currently 1, right? I'm going to put 1 over here. And then it is the case that I will say R for result, larger than or equal to a j. So now, is this going to be true? Right. Okay, can everybody see that? Okay, hopefully you're able to judge this, right? I'll just do the first one for you. So now we know that currently result is being set to 20. And now, what's the size for this particular range over here? What's the size? Just 1, right? Because A dot lower is simply just 1. And then also between 1 and 1, just 1. So that means 20 itself is larger than or equal to A1, which is also 20, right? So 20 larger than or equal to 20, so that's simply just true. So the looping variance for the first, before we enter the first iteration will be true. And then if we plug in the value for I, which is 1, and then we're going to evaluate the exit condition over here, right? Over here. So now 1 larger than A dot upper, which is 4, is false. That means we don't exit just yet, okay? Now, so that means that will be false, and variant is not an issue. Okay, let's forget about a variant for now. Okay, we'll get to the variant in the second version. Are we okay so far? So that means before we enter the very first iteration, we know that the looping variant is established for the first time. Okay, so no problem so far. So, Sammy, is that what you meant? Or you meant at the end of the first iteration? Why don't we try? So what you're suggesting is, at the end of the first iteration, we're gonna have some looping variant violation. Let's try to see if that's the case. So now let's just get an idea what's gonna be done by the body of the loop for the very first iteration. So now AI at the moment, let me use green for the first iteration. AI at the moment, as we said, is gonna be A1, which is 20, right? A result has also been established as 20, right? So 20 larger than 20 will be false. That means we don't replace that. Okay, so maximum remains to be 20, the result. And then I is going to be incremented from 1 to 2. Agree? So now that means at the end of the first iteration, we're going to get I incremented to 2. And now we're going to go back basically to check this invariance again. Okay? So now if invariance simply just I is now 2. That means the one we're going to check, let me use a different color, or let me use pink, yeah, just say pink. So now I's value is 2, and what about the result? After the first iteration, it remains to be 20, right? So it hasn't changed really. So that means 20 is still there. Now what about the looping variance? If we try the looping variance over there, what we are checking really is, I'll put it here, that means for every j such that a dot lower less than or equal to j, less than or equal to, now I is 2. So that means we covered 2 elements there. So now it is the case that result is larger than or equal to a, j. Now we know that this particular range has the size 2, right? We're going to consider element 1 and element 2. And now R is 20, right? Remains to be 20 over here. Now 20 is larger than or equal to 20. 20 is larger than or equal to 10. So that's fine. So looping variance seems to be okay after the end of the first iteration. Okay, and then I'll take questions. Yes? Yes, but since we are talking about this particular example, right? So that's why I want to use an example to show you. Similarly, if in the exam, if I give you a particular looping variant and say, now illustrate whether the looping variant is good or bad using this particular example. If you think the looping variant is good, that means you can satisfy looping variant until the exit of the loop. If you don't think it is okay, you're going to illustrate to me exactly when it's going to fail. Okay? So now the point is, at the end of the first iteration, it seems like the looping variant is still satisfied for this particular example. Right? Now let's go on a little bit further. Okay? So now we know when I is equal to 2, we know that when I is equal to 2, if we evaluate the same exit condition over here, 2 larger than 4 will be false. That means we don't exit just yet. Okay, so we don't exit just yet. Let's not worry about the variance. So now what we should do is we should really go into the second iteration. So what should we do for the second iteration? What we should do is something like this. Let me use orange. So now for the second iteration, what we should do is, at the moment, AI, which will be A2. A2 in this case is 10. Agree? And then in that case, result is still 20, right? You can see this relation here does not hold, so we don't replace that. Okay? And then we're going to increment the value of I from 2 to 3. Okay? And now after that, so that means I will be 3 at the end of the second iteration. Now, if we try to evaluate, what will be the result before I say that? What should be the result in this case? 20. Thank you. I agree. Because as you can see, why 20? Because you can see 10 larger than 20 still remain to be false. So that's why it's not going there. Good. Now, if we now try to evaluate the looping variance for the third time at the end of the second iteration, what's going to happen here? It's going to be false, right? Okay. If you think so, that's good, but let's see exactly how. That's exactly how you should explain in the exam. So now over here, for the third iteration, the same looping variant, we're going to say for every j such that a dot lower less than or equal to j less than or equal to, in this case, 3. And then it is the case that result larger than or equal to aj. And now we know that the value, the number of values in this particular range will be 3, right? So that means we can consider this, this, and this. And now what's R? 20. So now, is 20 larger than or equal to 20? Yes. 20 larger than or equal to 10? Yes. But larger than or equal to 40? No. So that's how you felt. So not really. That's exactly how you felt. It's very, very precise. Okay, that's the precision I would like you to achieve. Okay, so what's really the problem here for the looping variance? The intuition is when you say less than or equal to j, sorry, less than or equal to I for the looping variance over here, you're already including the I value that is just about to be handled in the next iteration. That's not supposed to be the case. So now how do we fix it? Well, you can say less than I, or you can say less than or equal to I minus 1. Either way. Yeah.
We did I become equal to I plus 1 before the if in the loop.
Interesting. You're basically asking, what if you simply change this to over here? Interesting, okay? I would say leave this as an exercise for you guys. I can tell you that the result may not be the same. Okay, so now exercise for you, okay? So exercise is like this. Change I is assigned to I plus 1 to line 1 of the body of the loop. Then let's see what happened. Okay, that's the exercise for everybody. Intuitively, it seems to be working. It seems to be, but I want you to check. All right. Yeah, that's something you can expect. For example, on the exam. But I'll talk more details. Yeah. Yes.
So we can change this by for the looping variant. We can make it less than I, right?
You can, yeah, you can either say it's less than I, or you can say less than or equal to I minus 1.
Okay, so how are you going to make it in the across?
Oh, good question. So the way you can make it in the across would be, you can see over here, rather than I over here, right? You can simply say I minus 1. Well, pretty much like how you did it. Yeah, you cannot really say less than, but you got to give an inclusive range, right? Yeah. Yes?
For the first iteration when I is equal to 1,
Uh-huh.
it's going from 1 to 0. So it won't even go into that? Into the
Okay, are you talking about the old implementation or the new one?
new one with I minus 1 in that variant.
Over here, I see what you mean. That's a very good question. Let's say this. Basically, okay, the question is as follows. Let's say we did change the invariant to be the correct one. Let's say we still keep the I is assigned to I plus 1 as the second line. We don't change it as you suggested. That'll be exercise. Now let's say we change the I over here to be I minus 1. That's the correct looping variant. But let's see why it will be correct. Okay? So now what's going to happen is we know that initially I would just be A dot lower, which is just 1. Right? That means when we evaluate this looping variance for the very first time, what do we have? I'll write it down. What we have is, logically speaking, for every j such that A dot lower, which is 1, right? 1 less than or equal to j, and then less than or equal to, in this case, 1 minus 1, which would be 0, right? And then we have result larger than or equal to aj. Okay? Now, if I have, now let's be, nothing wrong up to now. Okay? What would this reduce to be? When I say j is larger than or equal to 1, but less than or equal to 0. Empty set, but this is more like a predicate, right? It's specifying the range. Don't you agree this can be reduced just to false? Which means there's no such j that can satisfy this predicate over here. Are we okay with this so far? Okay. Now, let's talk a little bit about 1090. Just a little bit. Hopefully that will help you. When you have for every, let's say, x, such that you have some range on X, it is the case, some predicate X, right, over here, right? Okay, now, we are basically asking what if we have a special case where this is simply just false, right? That's what we're asking. Now, let's go to a little bit one step further, which I'm pretty sure you know. In that, we know that this is equivalent to, for every X, how can we move the range into the predicate part, property part? It's as if we say Rx implies Px. Okay? Now, what if we know already the antecedent is simply just false? The implication is simply just true, right? So that means when the range is simply just empty, the for all over here is simply just true, trivially. So that means the loop invariant that we just induced over here, when we have I minus 1, for the very first time we check it, the range will just evaluate to just false, which will make the for all trivially true. Okay? Guys, that make sense? Good question. The question was, similar to this, let me use this, green. What if I have, let's say, there exists X such that false, and then P of X. Well, if you, again, recall from 1090, this is equivalent to there exists X, whatever you have over here, false and P of X, right? In that case, false and anything will be just false. So overall, it's just false. Okay? Let me just say one more thing. Intuitively, why in the case where the range is actually empty, you will actually get true overall? Intuitively, you can think in this way. In this case, the range is simply just empty because we got just false over here, right? Range is empty for the universal quantification. Means we cannot find any witness of violation. Okay, you simply cannot find any witness to prove that the property may be violated. If you cannot, the property must be correct, must be satisfied. Symmetrically, in this case over here, the range is also empty over here, right? So now this is a similar argument. Range is empty means we cannot find any witness of satisfaction. Since you cannot find anything that will satisfy the property, so they exist should just be trivially false. Okay? Just a little bit intuition to the properties. Okay, any question about this, about the looping variance, right? So of course, the reason we're talking about this simply because for the looping variance we have from the previous slides, the very special case for the first time, when the range is reevaluated to be empty, you got trivially true. Okay? Guys, any questions about this? Okay, are we okay with this example? Good. So that's about the looping variance. Okay, so now if I give you something like this, that's something I will expect you to explain. Okay, so now looping variant will just be false. Okay, it will be violated. So now one more version to talk about. Let's have a look at the second version over here. In the second version there, you can see that I already fixed the looping variance, the upper bound there to be I minus 1. So looping variance is no longer the issue. Okay, what I want you to look at is the variance over here. Okay, I can tell you there's something wrong with the variance. Okay, yeah. But what's wrong? And when would you get a loop variance violation? That's the question. You get a loop variance violation if either because from one iteration to another, the value for the variance does not strictly decrease. That's one cause of problem. The second cause of problem is when you try to exit from the loop, after a particular end of the iteration, the loop variant evaluates to something that's negative. So these are the only two causes. Is it the first cause or second cause? Okay. By the way, how do you make the first cause satisfy? Yeah. For the first cause, simply means the loop variant doesn't really decrease its value. You can just get rid of I is assigned to I plus 1. Okay. I think we talked about it briefly last time. Okay. Now let's focus on this particular one. So we know that the problem basically is, if you actually have this particular loop variance, eventually it is going to evaluate to something that's negative. Okay? Can you see which iteration is that?
The very first iteration, because like, you know,
Are you sure?
Upper is 0 at the very first.
Why don't we try? Okay, let's say this. Well, actually, you already got some hints from the table. Let's go over the table very quickly, okay? Initialization, a dot lower would just be 1, agree? So we start with I being 1 before the first iteration. And now, so we don't really notice one thing. We don't really evaluate the loop variance before we enter the loop. Notice one thing. That's why I put a not applicable here. At the end of the first iteration, I gets incremented to 2, right? So now to evaluate the loop variant, we don't have to worry about every variable. We only worry about the variable that the loop variant depends, in which case it's a dot upper and also I. A dot upper doesn't really change because we don't really grow the array or shrink the array. So now what about at the end of the first iteration, as you predicted? In that case, a dot upper, which is always 4, 4 minus 2 will just give you 2, which is okay, right? 2 is still larger than equal to 0, not a problem. Okay, and then you can see that the way we grow the loop counter over here from 2 to 3, 3 to 4, right? So it always grows, okay? It's because the i's value keeps growing, that means the loop variance keep decreasing, okay? Now I can already tell you at the fourth iteration, at the end of that, we're gonna have some trouble, okay? Because at the end of the third iteration, what we have is the value for I is 4. Well, actually, at the end of the third, we got 4. At the end of the fourth, we go from 4 to 5. In which case, what will be the value for loop variance? -1, exactly. Once we got -1, that means you got loop variant violation. Okay, that's exactly what happened. Okay, so that's just another case where the contract for the loop might be violated. Okay, we talk about two cases, right? Either you have a violation for loop invariance, or you might have violation for the loop variance. Okay. Guys, any questions about this? Okay, good. If you have no question about this, let's go on. Okay, when you see the slides, basically got 3 versions. The first 2 versions are wrong, which we just talked about. The third version is where the invariance and variance are fixed. Okay, you can look at the correct version by yourself. Okay, okay, now let's go to the final part for this particular loop correctness. Okay, topic. So now we talk about loop invariance, we talk about loop variance, but now how do we prove the correctness of the loops? Okay, as I said before, correctness is really about there are 2 separation of concern. Okay, this is 2 separate concerns. Okay, let's say we got a loop like this. Okay, again, you got the loop start with some precondition Q, and then at the end of the loop, you would like to establish some post-condition R, let's say. Now, also you got invariance, you got variance. Now, we want to learn about what kind of conditions you need to prove in order to prove that, number 1, the loop terminates. Number 2, assuming that the loop terminates, is it going to, upon the termination, establish the post-condition? So these are 2 concerns. So we want to prove total correctness. So now, that's why we'll see different conditions to formulate. Okay, let's do one by one. So now, a loop is partially correct if you say, given the precondition Q, okay, let's go one by one. Now, if you look at that, given the precondition Q, and then the initialization part over here is going to establish the loop invariance I. Okay, that's the first condition we want to establish. Okay, let me just switch the iPad. In total, we got 5 different conditions for you to prove. Okay, but I already covered them, so we're gonna figure out how to do that all together. Okay, and then we'll see examples on the side. So now, first of all, we got something about partial correctness. In the case of partial correctness, we don't worry about termination. So we worry about termination separately. Okay? So now for the very first one, given the precondition Q, we want to say the initialization step, which is over here, is going to establish the loop invariance. So now, how do we formulate this condition over here? Using a Hort triple. For any particular Hort triple, what do we have? We have a particular precondition, we have some code, we have some postcondition, right? I'll do this one together for you, okay? For this one here, that means we're going to start with the precondition over here, and this is the code, and this is something we would like to establish, right? It would be as easy as just like that. Okay, starting with the precondition for the loop, and then by doing the initialization of the loop, we're going to establish the loop invariant for the first time. Okay, let's do the second one together. Okay, second one. What does the second one say? The second one simply says the following. So at the end of the body of the loop, if not yet to exit, which means we are still going for the next iteration, loop invariant is simply just maintained. Basically, we're saying the following. Assuming that we're starting with the current iteration where the loop invariance is satisfied, and then we execute the body of the loop, and then afterwards, we want to make sure the loop invariance is maintained. That's something we want to make sure. But how do we do that? Anybody want to try? What we want to have is basically something similar to this. We're going to have this format over here. Put something here, and put something over here. Okay, just tell me the parts. Yeah, go ahead.
Precondition is I.
Precondition is I. Okay, I agree. Let's put I here.
Postcondition is the looping invariant.
I again, right? Somehow, right?
Yeah.
That means you start with I. You want to make sure I is maintained afterwards. Good. What about the implementation part? Just implementation. Right, not exit will go somewhere, but we'll get there. Okay. But you are saying somehow we start with the loop invariance. We want to make sure at the end of the execution of something, loop invariance is still maintained. What should that be? Body, right? Okay. Exactly over here. Put S body here. It's pretty much right. But we want to make sure we are only handling the case where it's not yet to exit. So we want to say basically like this. Loop invariance, and then not the case that B is true. Okay, that's basically what we want to have. Okay, are we okay with this? Okay, you can see that what we're trying to do is you try to read the English first, and we try to formulate it using math. Okay. All right, let's see another one for partial correctness. What about the third one? The third one over here, if we are ready to exit and the loop invariance maintained so far, and now the post condition is going to be established. Let me give you a little bit hints. To formulate this question here, to formulate this condition here, you do not need a Hort triple. You do not need it because there's no code to be executed over here, right? There's no code. There's no body of the loop. You just need some simple logics that you learned from 1019. Yes, yeah, William, go first. Okay, one moment. I'm going to write down exactly what you're saying. Okay, you're talking about invariance I and B. Okay, that means we're ready to exit. What implies R? That's a post condition over here, right? Okay, maybe that's what you're thinking about. Yes. Okay, good. Exactly. Okay, good. It's not too bad. Basically, you want to understand what's really in the English, how you formulate it as well. Yeah.
This is a good question. So basically, we're forming templates.
Yeah, basically the rules over here that I'm trying to formulate together with you. So these are the general principles, regardless of what programs you're given. And we're going to apply these into the example we just talked about. We're going to see that. It's quite straightforward once you understand the rules. Okay, so this part here, nothing about termination. So now, how do we handle about termination? Remember, talk about two aspects. Number one, you want to make sure, let's go over one by one. Number one over here, let me use blue over here. We say, given the loop invariant and we are not yet to exit, we want to make sure the loop variance is always non-negative. you can see over here we do have some code to be executed, so we need a whole triple, right? Anybody want to try? Okay, try. One moment, let me write it down. Okay, what I will do is I'll use maybe a blue here. Okay, it's going to be a whole triple, something here and something here. So what should I put?
So I and not B.
And not yet to exit, I agree, and not B.
And then for the implementation of S body.
S body.
And then
Oh, not, yeah, not negative, right? It's not negative. So larger than or equal to 0. Okay, that's pretty good. Let's see if that's the case. Good. Fantastic. Let's do the next one, last one. Okay, and then we'll do examples. The last one is basically like this. The last one, let's read it together. The last one is, given the looping variance has been maintained so far, and we are not yet to exit. And then we want to make sure the value of V has been strictly decremented. Okay, I'll give you a little bit hints. You may want to use a notation to denote the O value for the variance, right? You're going to use the O value and the new value. Pretty much like how you write a post condition. Okay? Now, I can tell you, you still need a whole triple. Okay, anybody? That's the last one we're going to do. Anybody at the back? Anybody want to try? Don't be shy. Nobody want to try? How about you? All right.
All right, so I,
Oh, one moment. So we're going to have something here, and something here. So what should I put here?
in the precondition, I is maintained.
Mm-hmm.
And loop is not exited, so it's not B.
Not and not B.
And in the implementation part, it's S body.
Okay, good.
And in the post condition, it's V is equal to O V minus 1. Sorry, V is equal to O V minus 1.
Okay, you know what? I'll write it down exactly what you said. V is equal to old V minus 1. You're being a little bit too specific to the implementation we talk about, which is I is assigned to I plus 1. But what if I say I is assigned to I plus 2? In that case, you will violate this condition quite easily, right? You want to make it as general as possible.
Yes, sir.
Yep, exactly. What you really want to say is something like this. You want to say V over here, the new value is strictly less than old V. Okay, good. But I'm glad you mentioned that, okay? Okay, that's exactly what you have. Okay, but I'm just using V0, right? Remember we said before, if you use 0, that means the same copy of the variable are in the pre-states. Okay, guys, any question about these 5 conditions? Yes.
When you say decrements, that doesn't strictly mean.
Oh yeah, when I say decrement, not really like I minus minus or yeah, I'm not being very programming. Yeah. Mm-hmm. Yeah. Decreases. How about that? Yeah, maybe I should say decreases. Yeah. Okay, if no questions, I would say let's do some very quick go through. Okay, let's just do one example, a few examples together. Okay. Now let's go on to here. Okay, you can see we look at the same example over here, and then we got a 5 conditions to formulate, right? Let's just do 1 or 2 together. I'll choose 2. Okay, and then for the rest you can see on the slides. Let's do the first one first. Yes. Sorry. Thank you. Yes. Let's do the initialization first. For the initialization, we are saying that given the precondition for the loop, and then doing the initialization part, we're going to establish loop invariance, right? So now how do we do that? For this particular loop or feature over here, what's the precondition for the feature? Well, there's no require. So it's as if it was true. Okay, good. So what I would do is I'm going to say over here, I'll put true over here because there's no precondition as if it's true. And then I'm going to have this part being the body for the initialization, right? So I'm going to put I is assigned to a dot lower followed by result is assigned to a at position I. So what about the post condition? Basically, this part, right? The looping variance, right? Okay? If I ask you to write this on the exam, you're allowed to say this is Li. You can say Li. That's fine. Okay, but you get the idea. Are we okay with this? Okay, so now, without wasting your time, if you look at the slides, basically everything has been specified out for you. Let's just look at them very quickly. So these are the 5 conditions we just talked about. And then for this particular one, you will see that this is the one we just talked about, right? And then how do you maintain the looping variance, right? You start with the looping variant and not the exit condition with the body of the loop, and then you got this. Okay, you get the idea. Any question about this particular example of formulating your loop code into Hoare triple, the 5 conditions? Okay. If no questions, okay. So what you should do is you should really try to prove to the best preparation for the exam, try to prove all of them. I already posted the most difficult one to prove is number 2. How do you prove the maintenance of the looping variance? I already posted the solution on the course website. Maybe try yourself before you look at that. Okay? And now, let me just do just one of them with you. Okay? The easy one. Okay? The hard one, I'll leave that to you. Okay? But you got a solution already. Now, let's look at this one. How do you prove it? How do you prove it? Yeah. You got a Hoare triple, basically, right? How do you prove a Hoare triple? Calculate weakest precondition, right? Let's calculate weakest precondition. Okay? Let's do that. So we're going to say the WP for I is assigned to A dot lower followed by result is assigned to AI over here. It's going to establish the looping variance over here, right? You're going to write it down. For every J, A dot, I'll say L dot lower less than or equal to J less than I, such that I'll say R for result larger than or equal to A, J. That's the WP. Okay? Now, first of all, we have to apply the WP rule for sequential composition. Agree? So what we'll do is a sequential composition over here. So what I would say is equal to, so now WP rule for sequential composition. So what I would get is, I'm going to say WP over here. I assume you know how to do it. I'll just do it, write it down. I is assigned to A dot lower, and now it's going to be the WP over here for result is assigned to AI, for that to establish for every J, A dot lower less than or equal to I less than I, and R larger than or equal to AJ. Okay, so far so good? Now, what's the next step? We should do the weakest precondition. Which rule should we apply? For what? Assignment, right? Since that sequential composition has been gotten rid of already, so we just do the assignments. Okay? So what we'll do is we'll say over here, basically we're gonna replace every occurrence of result by AI, right? In this particular post condition, that's what we will do. Okay, we're gonna say WP rule for assignments. Okay, so now basically you can see the only occurrence of result is going to be over here, right? Replace that by AI. Agree? Okay, so let's do it. So what I will get is WP over here, I is assigned to A dot lower, which is going to establish the following. It's going to be for every J such that A dot lower less than or equal to J less than I, and then we have AI, right? AI over here larger than or equal to AJ. Good. Some of you might already seen the trick to get this trivially true. If you haven't, we'll go on. We're almost there. So now, should we apply any more WP rule? We should, because WP is still there, right? You want to get rid of it eventually. So WP for assignment. Thank you. So let's do it. What I would do is I would say, okay, WP rule for assignments. Okay, and then what I would do is I'm going to replace every occurrence of I by a dot lower. And the occurrence of I can be over here and over here. Right? Let's do it. So that means I can get rid of the WP already. So I can say for every j such that a dot lower less than or equal to j less than a dot lower over here, it is the case a at a dot lower larger than or equal to aj. And now what? I can tell you that this expression is trivially true. But in the exam, you cannot just tell me it's trivially true, right? Sometimes it may not be so trivial to us, right? So you want to justify a little bit. Can anybody justify why it's trivially true?
But there is another part of this, right? So the first part is calculated with this.
Oh yeah, I'm saying just for this particular one, I'm saying this predicate can be reduced to true. That's my point.
Oh, okay.
But why? Why can I reduce this part directly to true? Should I give you, you want to try? Yes.
J is always like the set that for all J such that
Mm-hmm.
A is less than or equal
Mm-hmm. Yeah, exactly.
to lower.
Yeah, basically we're talking about this particular range, right? Is it let's say a dot lower, just for example. Of course, a dot lower can be any number, right? Let's say a dot lower, for example, is just 1. A dot lower is simply just 1. Is it possible for you to find a number between 1? Well, basically, you're asking the following. Between 1 and 1. Is it possible? No. So that's reduced to false. And remember what we said before. When you actually got false over here, you get overall true. Okay? So that's how you prove it. So now we know that's false. So that's equivalent to true. So the right way for you to justify this is to say, for this part of the range predicate, it reduces to false. Because there's no such number that's in between, lower and lower in this way. Right? So that'll be false. And in the case of the universal quantification, if the range part is false, it goes to true, trivially. Right?
So if you had a dot lower is less than equal to j,
Uh-huh.
is less than equal to a dot lower.
In that case, that will be, of course, that will be just one element. Yeah, but for this particular one, remember the way we lay out our looping variant is we got strictly less than. That's why we do the replacement. Of course, if you got another sign, that's another story.
But you can't just do the trivially.
Then you cannot, for sure. In this case over here, because to really satisfy these two at the same time, there's no such number. That's why it's false, right? Okay, guys, are we okay with this? Okay, this one is not too bad, not too bad. Okay, but it will give you a feel about, get like a warm-up for part 2. Okay, so now I want to just, I do have something prepared for you. In order for you to prove this particular one, let's say this one is the only one that has no Hoare triple. How do you say that, given that looping variance has been maintained, and also the exit condition is actually true? That means we exit from the loop, and the post condition can be established. Okay, this one is rather interesting. I will give you a little bit hints. You can when you watch the recording. Okay, here's my hints. If you try to look at the following theorem, which you don't have to prove, I'm just giving this to you. Okay, if I know that P is stronger than Q, if I know that, that means if I put P over here as the range and Q here as the range, and I have this one here implies this one. Okay, that's a theorem. But let's see example to get some intuition. Let's say over here, this one here, if I got 1 less than equal to x, x is in between 1 and 10. And also this like that, right? So which range is stronger? Well, this one's stronger, right? Because apparently you can see this one implies that one, right? Hopefully you can see that, right? So you can think about this is more like a P, this is more like a Q. Okay, and then we got this relation over here. Okay, and then you can see the same thing for this particular example. So this is my hint to you. In order to prove this particular predicate over here, this is something you would need. Once you understand this particular theorem over here, You will just have to see exactly how each of them are being laid out. Then you can prove that quite easily. Okay, that's a hint to you. Okay?
The second one, isn't that last line wrong?
Yeah, the second one, okay. The second one, basically what I'm trying to do is, you can see, we know that this is stronger, right? So I'm just reversing the order. I'm trying to show you how the theorem can be maybe applied wrongly, right? Yeah, it's just a counter example to show you. If you get the relation in the wrong direction, then it will actually give you a counter example. Okay, that will be an exercise for you. Okay, something similar. Okay, and now another one. How do you prove that the loop variance stays non-negative? Okay, this one I want to again give you some hints very quickly. Okay, this is the post condition we would like to establish, right? You can see that this is a variant expression which depends on a the upper and also I, and also one is just a constant, right? So these two variables are the ones we care. However, you can see that over here in the precondition, we actually got two preconditions over here. We got a looping variance, and also we got the exit condition. So now here is a proof tip to help you. Okay, I'll show it to you. If you look at the slides over here, I'll point to you. If you look at the slides over here, I do have a proof tip for you over here. So what does that mean? That means if this is some Hort triple you want to establish, I'm given a precondition Q and P, and then I want to establish R. It will be sufficient for you to only use one of the preconditions. You don't have to use both of them. If you find any precondition not so relevant to the postcondition you want to prove, you can just discard that. And now, if you go back to this particular example, you might find that in order to prove this particular postcondition, one of these preconditions may not be so necessary. You can just get rid of them. That can simplify your proof a little bit. Okay, that's a hint to you. Once you get that tip implemented, it will be quite easy to prove. Okay, so I believe that's it. Guys, any questions? Okay, let's wrap up the course, and then we'll do the rest. Okay, something you have been looking forward to. Maybe not. I'm not too sure. All right, let's wrap up the course. Right. So what have we learned in this course? Definitely you learn about IFO. That's one thing, right? But that's very superficial. Very superficial. What we really want to teach you in this course, which I hope at least you pick up a little bit, is we want to learn about design principles, right? Especially, I want you to really think about, when we did lab number 1, we think about our contracts, especially how you can specify complete contracts in the post condition. We really want to say the contract is really a very strong binding for the supplier and the clients, right? So that's really something I want you to get used to. Even if you don't program in IFO anymore, if you go back to Java, go back to C#, you still want to really have this kind of a notion of contracts in your mind. That's something we want to program in your mind, really. Okay, and we're going to think about the code level. Not just the code, but more about design. Again, this course is about design. Okay, information hiding, okay, and single choice principle, open close principle, uniform access principle, right? Just to name a few that we talk about in this course. Okay, hopefully when you graduate from this course, at least you know what these principles are when you go to your job interview, right? Design patterns. We also talk about quite a few. I'm going to suggest actually not a book. Remember in the syllabus, you can look it up. In the course syllabus, there's one reference book for the design patterns. That's more like a catalog of other design patterns which we haven't covered. We only cover some important ones. We just cannot cover all of them. So maybe if you're interested, you can definitely study the rest of them beyond this course. Okay, just singleton iterator, states, composite, visitor, observer, event-driven design, undo, redo, and ETF, right? I'm just curious about this, Tell me which one you find the most interesting. I'm just curious. Visitor? Are you sure? Okay, I'll make sure you see in the exam. Okay. Yeah, actually I like visitor too. I also like it. I tell you what, when I was a student studying the visitor, even after the exam, I still cannot fully understand it. It's really after I teach it that I can really fully understand. So what's the best way if you learned about the patterns and how you can prepare for the exam? Well, form a study group. That's the best way, okay? That's advice for you. Okay, so that means in the exam, I might choose any of the 2 or 3 patterns to test you. Okay? 2 or 3, or 3 or 4, something like that. Okay, yeah, I'll get to a question about the exam. I'll get there, don't worry, I'll get there, yeah. All right, now I want to say one more thing. Now, let's go back to Java just for the moment before we end the course, okay? Summarize the course. This is some API you're very familiar with in Java, right? It's not IFO, it's Java, okay? Now, if you look at that, it's a very typical API to look at when you are new to a particular library, right? You look at that, okay, the class is generic. It got a generic element E, which we learned about. And also, it says that over here, the element type is simply just E, which might be instantiated to any reference type. Okay, nothing specific to IFO or Java. And then if you look at over here, I'll read it to you. Over here, they do have some description over here, an order collection and whatever, right? They got lots of description in English. Now, so far so good. You know, it's kind of a reasonable, informative description for you. Also using generics and also using, also have some intuitive overview for the class. Now, let's go a little bit further. If you go to at a method level, let's say you go to the set, for example. Let's say you go to a method called set. You simply got integer index and E elements. It simply said replaces the element at the specified position in this list with the specified elements, and then they say optional operation. I would say this description is somehow maybe reasonable, but are you sure you really understand it precisely? Like precisely what it is going to do? Sometimes it may not be, right? So what can you do? You have to test it to really write some small test cases and see exactly what the behavior is. However, if we know about contracts, if you look at the contract view, if the supplier does their job properly, the contract should tell you exactly in the post condition what this feature should really achieve. So this is something you can only do in terms of Java doc, informal description in Java, but not unlike what we learned in IFO. Okay, that's something I want to highlight as a difference. Okay, and then you can see a little bit more. If you look at the method summary, they will say, again, some informal description over here, and then they will tell you, they might give you some implementation-specific exceptions, okay? Unlike the precondition that we see, in this course. Again, this is nothing wrong with it. It's just at a different level of abstraction. This is more about implementation. What we learn in this course is more about design, right? Yes?
Could the returns part of the API be known as the post condition?
Yeah, of course. The return value over here, in our case, is just like a result, right? You can definitely specify result as part of the post condition. On the other hand, if you try to look at what we have learned in this course, this is something we have, right? You can actually have require ensure, and then you have the complete post condition like this, right? Okay, that's something we have to, we have shown you in this course. Hopefully you will pick up something from this. Okay, so precondition, post condition, class invariants, and also for loops, you even got loop invariant and variants. So these are the design ideas you have learned. Okay, just to mention quickly. Now, beyond this course, okay, just very quick. Beyond this course, what about you go back to a language which does not really support design by contract natively, like how we somehow criticize about Java in the first lecture. I would say you can still do something to by your efforts. Basically, just document your contracts, either maybe informally using Java doc, but you want to make sure somehow you are really writing some JUnit tests to really make sure you test the precondition and also test your post condition. That's how you can make sure every time you run your regression tests, all the contracts are really being checked at the runtime. Not as convenient as what we are doing in this course, but once you go to real world, that's maybe something you can maintain. Okay, and then math library. Let me say one more thing. The math library is something even more abstract, right? So you're forced somehow to think in terms of sequence, relation, and function, like in your lab number 5. So now I would say that's also a very nice design level construct for you to think about. Basically, the idea is whenever you're given some particular application, I would say the most general math type is relation. It's more like a graph, because many applications, as you learned in 2011, can be implemented using a graph. So once you get a design level sorted using a relation, you can easily refine that into a relation, right, in the math model. Well, it doesn't have to be a math model. Okay, anyway, just a very quick, you can also read it through the slides. Okay, you can definitely, if you think in terms of sequence, you can refine that into linked list or array. If you think in terms of function, you can refine that to hash table. If you think in terms of relation, refine that to graph. Basically, on the right-hand side over here, these are what you learned in 2011. And over here, sequence, function, relation is what you learned in this course. Okay, so they are somehow just belong to different levels of abstraction. All right. Okay, one more thing. Questions or you're fine? Okay. One more thing. If you really are interested in some design ideas, this is quite a nice book. Don't purchase that. Just check it out from the library. So this is quite an old book, but this is a book collecting a number of papers from a very renowned software engineer, David Parnas. Anyway, you don't have to know his name. So specifically, if you check out this book, especially you can look at tabular expressions. So this means you're going to do the design using two-dimensional tables. It's quite an interesting idea for design. If you're interested in this further, maybe take the software engineering requirements course at the 4th year. I'm not teaching it, but somebody else is teaching it. Okay, and also information hiding. They also got quite a bit of discussion on that. Okay, that'll be it for the course. Any questions for me? Yes. Yes. I mean about the exam, right? We'll talk about it. Yeah. I'll let you ask any question about the exam after this. Oh, just any question about the course itself before we talk about the exam. We're okay? Good. Let me stop the recording now. As I promised, right?